Hello everyone. Today I'm going to be going through a book in Robert Hartshorne's Algebraic geometry. This is a problem from his section of sheaves. I think it's 2.5.1 or something. I'll put the actual problem list in the comments or whatever. But this is the first part. This helps answer parts A, B, C, but I only want to do part D for now, which is this part here. So I might do another video of part A, B, C, D, or etc. But this not now. I just want to focus on this. Before I even proceed, I want to show you the most important part of the video, and it's a cool image of Sheldon Cooper I found on Google. This is the most important part of the video, so you must take notes on this. He's going to be sitting here while I do this. Now, we need to read what's presented here. If we have the map, which is a morphism of ring spaces, and if F is an X module, and if E is a locally free Y module of finite rank, then there is a natural isomorphism as the push forward of F, push forward, bracket F, tensor, pull back of E, isomorphic to the push forward of F, tensored with a Y module, and here's your sheaf E. Now, we need to take out some crucial information here, and I'm going to highlight it. E is a locally free Y module of finite rank. This is extremely important for one or two reasons, and it's crucial to both the solution and also a trivial result I would like to go through. Now, we know that since E is a locally free Y module of finite rank, it must be isomorphic to a section of Y modules. Similarly, the dual of E is also isomorphic to the NY modules, which also implies E is isomorphic to the dual of E. Now, to proceed with this problem, I'm going to make several notes. I'm going to perform first the trivial calculation. So make sure you keep note of this part here, because I'm going to get rid of it now. Now, say we have, I'm going to use the purple marker to represent triviality. Is that, if that's how you spell it? Of this problem. So, I'm going to rewrite the formula here, but with the dual, with what we found E to be isomorphic to, which in this case is the section of Y modules. So from this, whoops, it's completely neglected from my writing, there we go. From this, we get the isomorphism, so here's our push forward of F, tensored, here's our Y, and our N Y modules. Now, a note to consider, with tensors, say if I have M tensored with like base R, with Rn, we know it's isomorphic to Mn, which applies to this problem here because we have a Y base. So we now know it's isomorphic to the push forward of F N. And if you want to be fancy, you can write it as the direct sum, so M equals 1, and your push forward of F. And the reason why, if you don't know the reason why it's isomorphic to the direct sum I wrote here, it's because n means n copies. So what it's basically doing is, imagine if I just wrote this. Here's my sum. There we get this. And just doing this like forever and ever. And I can just express it as this notation. This is a trivial result, and I thought it was cool, and I wanted to make note of it because it helps you kind of understand the problem. So, what we're going to do here now is actually solve the problem, and first we need to consider what we wrote before this part. Reason why we need to consider that is because if we replace E in the problem with its dual, we get this. Which implies that the push forward of F with our base change tensor is isomorphic to its dual. Now, what we need to consider is a very important result. What we need to consider is a very important. What we need to consider is a very important result, and that is for any locally free sheaf in any Y module, let's say G for this case, there then exists a natural isomorphism. Say I have like the dual tensor, here's my Y, here's my G. It's isomorphic to a sheaf base Y, my dual, and G. Applying this to the problem, we find that it's isomorphic to the sheaf Y. Here's its dual, and we write it with the push forward of F. Now, I would like to perform what's called adjunction. Now, in the context of push forwards and pullbacks, there exists an adjoint functor. So, what that means is I can effectively, so that implies there is in fact a natural map. Say I write my sheaf home Y, here's my dual, then that must mean its adjunction is the push forward our X and the pullback of E and F is left preserved. Now, remember what I said about that decomposition before? About how we made a note that, so in this case, it's with a X module, and we have E and F. We get the decomposition F with the pullback. Now, what does this look like? Well, it looks exactly what's in here, doesn't it? So, flipping, obviously, the tensor around to make it look like the problem, we find that with its decomposition, we get the push forward of F tensored with X with the pullback of E as the final, well, we could write it as dual, but we can also replace it with E. And that confirms there is a natural isomorphism through those properties of junction and conversion. Now this is a, like I said, it's an algebraic geometry problem, or I like to call it an algebraic freakometry problem. I don't really like how they write it though, but like, if blah 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 blah, then there's a natural isomorphism, and they say part D, it's like, are you asking me or are you telling me? But obviously it's asking you, but it just feels like it's trying to just go, yeah. It's like saying if there's 5 times 5, it equals 25. It doesn't, like, it's like. But when, like, then again, it's just, I guess, formality or whatever. I hope you enjoyed the video, and I need to. Nope, that's not it. Here is, nope. Where did I write? There we go. This is the formally typed out proof of this, what I wrote, and I talk about it through here. So, since E is a locally free sheaf of finite rank, one can denote the sheaf as a section, there, what I wrote before. Moreover, the dual doesn't affect the structure such that we get this. Applying this, we can observe the structure when replaced with the sections of Y modules that we get our trivial result I showed you before. I made a note, of this particular tensor product rule, and then, using what we wrote before, decomposition, here's our, example. Whoops, there's a typo there. That should be a F, not a G, but that's okay. Here we get our sheaf, and all together we get this, confirming the isomorphism. Note, we need to make sure that we are constantly stating that E is a locally free sheaf of finite rank, because the formula will only hold, like this natural isomorphism will only hold for sheaves of locally free rank, because if they do not meet these criteria, then it will fail on sheaves that obviously, like, don't meet it. So, and like I said here, the context of this solution slash proof relies heavily on the assumption that assumption slash assertion that each sheaf is locally free of rank. Don't use assumptions in math unless you're, like, designing something. That's the typed out proof if you really want to know. There it is all together. Take notes on it. I thought it was fun. I think I'll go through the other parts. I'll go through the other parts after, but this is just the first video I'm gonna make like this. Once again, this was the most important part of the video. I hope you made notes on that, because if you didn't, then good luck. Thank you for watching if you did get this far, and yeah, well, that's it.